I have a chance to tell you a few stories on technology and innovation. I had incredible luck to be at MIT, and I had incredible luck to get myself to MIT at some point. By the way, I tried getting into MIT as an undergraduate. I got waitlisted, and then I tried as a grad student, so I got rejected for that. So I snuck in as a professor, and I'm really lucky to be there, because at the end of the day, it's the ecosystem that we described before, the ecosystem of putting together the best ideas and driving them to the next stage that will allow you to make that great invention into innovation that benefits millions. I do look at it that way, by the way. For you and I to invent something new, it doesn't really take very much. All we need to do is just start talking to each other. And you'll hear something that I said, and I'll be amazed by something you said, and together we'll say, that actually could be a brand new idea. That invention, it's a eureka moment. It's just like Archimedes as he ran out of the bathtub. I mean, it took him a second to come up with the invention. And that's just the beginning of a 10-year journey, the innovation journey, that needs to follow. Well, often we miss that. Often we start with simply, this is the best thing since sliced bread, right? This must change the world. Well, it will not, until you actually rethink what the journey needs to actually look like. What is it that we need? What are the steps as we go along the way? So I will start with this image, an image of gold and silver. And you don't have to believe me that this is gold and silver, because it doesn't look anything like gold and silver would. You would expect gold and silver to be yellowish in gold or silverish in silver, and it's not. But I tell you, this is gold and silver. This is just how gold and silver look when you make them very, very small. If you take a chunk of gold and you slice it, and then you slice it again, and you keep slicing it until it gets to the scale of 10 nanometers. I'll tell you how big that is in a moment. It changes its optical properties. The electrons on that gold say, I'm actually on a very confined chunk of space. And electrons, just like photons, have a wavelength. You might have heard of that. We sometimes describe light as either waves or photons, particles. Turns out electrons, we often talk of them only as particles. They're also waves. Except the waves that can very, very short in distance. And unless you make a box in which they live extremely small, like a nanoparticle, you won't notice. So all that silver and gold do here is they make the boxes in which the electrons live so small that those electrons start behaving differently than they would in a bulk solid. Anything that's blue and green up there, that's a nanoparticle of silver, many, many of them swimming in a liquid of maybe methanol or ethanol, filling those vials with nanoparticles. Anything on the other side is a nanoparticle of gold, swimming in its own vial. Why are the colors looking different? Well, it depends how big the particle is. Change it from 10 to 11 to 12 nanometers, and you're going to find yourself changing the color. That sounds like a cool thing to know. Sounds like probably useless, unless you actually have an idea what to do with this, right? Well, we've known what to do with this for many, many years. All you needed to do is ask your grandma about the times past, and then she'll tell you about the stories from her grandma that she heard it from her own grandma, which is that back in the day, you would go and melt glass, and you would go to the left side of the mountain that the great-great-grandma told you to go to and get the right chunk of rock, put it in the molten glass, add just the right amount of horse's hair and a little bit of cow's milk, do the right chant, and before you knew it, 2 hours later, you would find yourself having a beautiful, beautiful, solidified blue, green, or red piece of glass, known as a stained glass back in the day. All that the nanotechnologists of the Middle Ages did is they would take chunks of gold and silver and make nanoparticles out of them. consequently changing the reflectance of the gold and silver inside the glass. That is why the stained glass windows don't fade. They keep on reflecting the same color year and century after century. Now, that was what happened following the grandma stories from a few hundred years ago. Today, what I would say is that you made a nanoparticle of metal, hence its plasmon resonance shifted from visible into the far side of the visible spectrum, causing the electromagnetic radiation incident on it to change its reflective property. Right? I mean, that's a whole bunch of jargon that now we can insert into the physical understanding of this chunk of matter that then can allow us maybe to make the next useful technology. Well, what could that be? Well, if you're in the lab of Professor Lee Gerke, a biologist at MIT, he'll tell you this is a really good way to detect Ebola, West Nile, dengue, Zika, and even COVID-19. How is that? Well, I told you that a nanoparticle of silver will change its color. Is it 10 or 11 or 12 nanometers in size? What if I had a nanoparticle of silver and I added to it a molecular layer, molecules that are 1 nanometer long, kind of like tennis ball, you know, fuzzy on the outside, solid on the inside. So there are these little ligands, we call them, that are hanging out. And depending on what molecule I choose to attach to the nanoparticle of silver, a different virus will choose to attach to the nanoparticle. There are molecules that are specific for Zika, specific for West Nile. You can't catch the whole COVID-19, so instead what you would do, you would break up COVID-19 and catch the proteins that are inside it, kind of like the guts of it. Well, if the attachment happens, that nanoparticle now is a little bit bigger. It's nanoparticle plus the chunk of matter, a virus. The electrons inside the nanoparticle now say, I have other places to go. I'm not confined only inside the box of the nanoparticle. I can spread myself a little bit now into the virus as well. Result is that the color of the nanoparticles changes. And you can now say, well, how can I make this into a technology? Actually, all you need is a piece of paper, paint it with these nanoparticles, as it's done over here. You can't see the nanoparticles until the binding event happens. How do you make a binding event? Well, paper is a microcapillary medium. All that means is that if you spill a cup of coffee, or a drop of coffee on it, it's going to spread, right? And you get coffee rings. You've seen this, right? So if you put a drop of blood on it, it's going to spread. And whatever was inside the blood will find its way in the far reaches of this paper. If whatever was in the blood reaches the nanoparticles, and there happens to be Zika in your blood, and the binding event happens, the nanoparticles start looking colored. It takes about 20 minutes, I'm told, to actually do the test. Why is this really a big deal? Well, West Nile has been found, for example, in deep villages of Africa. To reach a village in Africa and test inhabitants for the presence of viruses in their blood, you need to bring a few medical doctors, a refrigerator on your back, and then, since there are no paved roads, carry this into the village a day away. Once you reach the village, you have to draw the blood of all the villagers, refrigerate it, make sure the refrigerator doesn't fail, and carry it back to the town you came from so you can analyze the blood samples, and once the results come in, walk back to the village to go and tell them who is infected, who isn't. A couple of days of work, at least. And by that time, anyone who's infected could have spread the disease a little bit further. This, you have little strips of paper. They don't require refrigeration. They just require eventually for you to put a drop of blood of every one of the patients that you want to test. 20 minutes later, you'll get the results. It can be transformational. And all it's counting on is a little bit of nanotechnology we've known about indirectly through the stained glass windows. We have really understood over the last few decades of understanding how to manage nanoscale. And now we can start asking, how do I actually implement a new practical technology out of it? By bringing the brilliance of biology, the brilliance of material science and optical physics, so I can finally actually make a new testing that could not be done before. Nanoscale is very small, and I didn't yet describe to you how small it is. The fact I'm going to just leave you with is to say we can manage it really well. I can show you a nanoscale in a lab in a matter of minutes. If you're an undergraduate student and would like to learn how to use our microscopes, Give us a day, and we'll teach you a whole bunch of techniques. Give us an hour, we'll teach you a couple of techniques. And then you can start seeing the nanoscale and thinking about how to change the world with it. A nanometer is 1/billionth of a meter. Meter is yay big. So a hair, those of you who still have it, a hair is about 100,000 nanometers in width. Also, let's say 100 microns. That's another way to put it. A width of a hair to a width of a house is just about the same ratio as a nanometer is to a width of a hair. So it's very, very small. And yet it's a dimension we can routinely access by most inexperienced of us. It really doesn't take much because we finally have the tools to see how nanoscale truly looks. The one remarkable thing about that is that now that we know how nanoscale looks, we can reimagine many, many other ideas. But you, as the experimentalist that you are, although you might have not known, you happen to encounter, experience, and deal with nanoscale every day of your existence, like billions of times. And you don't really think of it. You just say, no biggie. I'm a bona fide nanotechnologist, I know it. And you do it any single time that you smell your cup of coffee. I can ask you, okay, so there's a cup of coffee, it's smelling really good. And you're saying, well, it's a coffee, without even tasting it, you know that. Well, how come you know that? I mean, what gives? Say again? The smell, yeah, okay. But wait a second, if I'm smelling my cup of coffee and my cup of coffee is here and my nose is here, well, it must be there's something left the cup of coffee to reach my nose, right? That's like the only way to explain. I don't know how else to explain it. And yes, you're right. Something left the cup of coffee. How big is the thing that left your coffee? Any thoughts? 1 nanometer. By the way, anytime I ask a question, 1 nanometer is a really good answer. So yes, indeed, it's 1 nanometer. And that's like 20 atoms put together. That's what 1 nanometer is. And it left this cup of coffee. Why did it leave a cup of coffee? Well, it's small enough. I mean, I can ask you, why does anything not stay in a cup of coffee? I mean, how come liquids stay together or not? Well, whenever you have small items like water or coffee smell, it's a very small molecule. The only reason why it ever stayed in a cup of coffee is because it was electrostatically attracted to the cup of coffee, so-called van der Waals forces you might have heard of a while ago. And once in a while, the molecules at the very top get bumped by the molecules from underneath, and they kind of fly away and make a vapor of whatever is the smell of the coffee. The smaller the molecule, the more likely it's going to be bumped out. It's less sticky, less willing to stay where it started. So, wait, did you just say I smelled 1 nanometer size molecule? Doesn't that imply that my nose is filled with nanoscale receptors? Yeah. As a matter of fact, let's just show you a few pictures here. So it's always good to have a yardstick. So that is 0.3 nano, in United States we use point rather than comma, okay? Just so you know. So 1/3 of a nanometer, that's a benzene molecule. Benzene is often drawn, it's assumed that on every corner there is a carbon. So to make things simpler, we kind of draw the simplified diagrams. So benzene itself is about 0.3 nanometers in size. And here are some molecules you might encounter. If you're smelling, this is drugs, first of all. And then we're going to go to smells in a moment. Just like the smells, which also happen to be nanoscale, any drug you ever encounter happens to be nanoscale in size. A molecule of aspirin is 1 nanometer, thank you. And I have a picture of it up there. Again, I'm using the yardstick of benzene as the yardstick to actually show you that. The ibuprofen, what helps us when we have achy muscles, again, about 1 nanometer, vitamins A, B, C, D, just about 1 nanometer in size, maybe 2. So are, the cocaine and LSD. There are other molecules, again, 1 nanometer in size. Our body continuously interacts with nanoscale objects. We use these nanoscale objects because we want to get healthier or and sometimes not so much. But it is the nanoscale that allows us to go ahead and define the functionality of these objects. Back many years ago, we didn't know about DNA. DNA is very narrow. DNA is only 2 nanometers wide. Back in the late 1800s, 1869, someone recommended that maybe inside our cells that you could see under a microscope, the regular optical microscope, regular cells, it looks like there was other kind of goo living inside it. And someone said that maybe inside this goo is something that defines us, that defines me versus you versus everyone else. They didn't know it's DNA, but they made a guess. And then they took about 84 years to get this X-ray diffraction image by Rosalind Franklin. It's an odd image. A bunch of spots that make kind of like letter X. This is not a usual way to get, this is not a usual diffraction image to see. Whenever you see a diffraction image, you see typically a square pattern, a rectangular pattern of dots, not a crossing pattern of dots, which would made it very, very mysterious. And it was suggested by Watson and Crick that maybe there is a molecule inside us, a twisted molecule, that, let's call it DNA. Now, there are these two guys, Watson and Crick, saying to the world, inside every one of our cells, there's this twisted molecule. It's really important. Who believes them, by the way? Anyone? Now we do. Back then, there could be more explanations. I mean, could be, I don't know, could be accidentally 2 molecules sitting orthogonal to each other. It doesn't have to be this one. It took about a decade, right? Maybe more. Martha actually knows this story as opposed to me telling it. For anyone actually to believe it, add 84 years to that, and we're talking nearly 100 years to get some amount of confidence that DNA does exist inside our cells and happens to be twisted. Today, you can ask a new grad student, you just learned how to use scanning tunneling microscope. Go ahead and take one of those cells and break it up and spread whatever the guts of the cells are and go find for me DNA. Take an image. 2 to 3 hours later, you might get an image like this. Does that look like a twisted molecule? Maybe, kind of. Maybe spend 2 more hours and get me another 5 or 6 images. It won't take more than a week, more than a day, for me to actually comfortably say, looks like there's this twisted molecule in there. The tools of today allow us to shrink 100 years of discovery by many, many people into a day or a week of work by one grad student, knowing what we're looking for. Something that is inside the cells. Now, if this is the first image I've seen, I wouldn't know it's important. However, I can still see it. I don't have to make a guess about it. It's because the tools of today finally let us see the nanoscale and reimagine what can we do with it. Any thoughts on what was the first moment in time that humans saw atoms? I'm not talking about surmised that there might be something called atoms inside our matter, but actually physically saw a circle or a bump and said, that's a bump image of an atom. Any thoughts? What was the year? Or what was the century? Any answer is fine, and 1 nanometer will not work here, so. Any thoughts? Yeah. 20th century, 19th, 17th century? What century do we think? Let's narrow it down to century. 20th century, okay. First half of the 20th century, later half of the 20th century? Second half, okay. Let's zoom in one more time. 1980s, 1990s, 1970s. At the end of 80s, scanning tunneling microscopy was invented. There were some images before in the 60s and 70s that said maybe that's an atom, but not with confidence. In the 1980s was the first time we had a technology known scanning tunneling microscopy that allowed us to actually see individual atoms. Images of how they hexagonally close pack on graphite, or how they rearrange themselves in a weird way on silicon in so-called 7x7 patterns, Or they make these little mountains here and there that never before imagined, but here you can finally see the images of. So this was late 1980s. The rest of, done by IBM Zurich. What do you think the rest of us scientists, I wasn't much of a scientist back then, but what do you think the rest of us were thinking about? Well, they saw atoms using that particular tool they just made. I want to see atoms too. And all we did in the 1990s is try to reproduce their experiments because it was so cool to see atoms, see more atoms and more atoms here. That gets us to like the end of the 1990s, and people in IBM Almaden say, hey, I can actually pick an atom and move it a little bit to the left. I figured how to do this. Don Eigler's group did. And they started making this thing called quantum corrals, which is just an atom and another one and another one. Really cool. You can make any image you want, by the way. Useful? No, not useful. And scientifically cool. And actually, also, it was done on a chunk of metal, so you can actually make little islands of electrons, so-called corrals. Corral the electrons and see them kind of sloshing back and forth, proving that everything we predicted the quantum mechanics should give us was actually true. Not actually discovering anything new, but giving us a tremendous boost of confidence that all the other things we were surmising might be true are actually true. And opening up vistas we never actually saw before, because there were a few things we forgot to mention when we were doing initial guesses of how the world truly looks. This is now early 2000s, maybe 2010s. That was, by the way, just to get you calibrated, like a decade ago. Yeah. It's about a decade that we finally have the tools to truly see the nanoscale and truly rethink what can that do for us. There are some technologies in the meanwhile that we invented and few things that truly made a difference, but many, many more are coming. We are at the dawn of the nano age. We live in a digital age, and it is awesome to be able to say, I understand how to program that computer, but I'll also tell you, fundamentally, that computer can be 10,000 times more energy efficient than it is today. And it's not going to happen because I write a better Python code. It's going to happen because I reimagine the matter and the way I can use it. We also think we can maybe even more than 10,000 times energy efficient if we use completely new paradigms. Not just quantum computing, but a variety of other digital computing paradigms have nothing to do with today's semiconductors. Wishful thinking. We have ideas, we have first demonstrations of it, but time will tell. It's instruments like this one that for the first time allow us to actually see how biology works. DNA was awesome to see, or call it sequence. One thing that was always stunned me kind of as an electrical engineer, every one of my cells has the same DNA, and yet some of my cells express themselves as a brain, and some of them express themselves as a kidney, and other ones are my skin, but they all have the same DNA. I mean, what is it about them that makes them different? Well, it's not just the sequence, it's also the mechanical shape, the folding of the DNA that also matters. And I told you DNA is 2 nanometers wide, so unless I can actually see how it truly looks down the nanoscale, I won't be able to tell you what that cell is going to turn into. Nor will I be able to tell you maybe how to make a medical solution, that nanometer scale aspirin that needs to fit in a particular nook and cranny of the protein and hopefully fix it, or indeed alleviate whatever it is I'm trying to alleviate medically. This is a picture of one of those proteins. Every one of those little bumps is an atom. We can now make these images. This was unimaginable a decade ago, the way we are doing it right now. And if you want to know more about how it works, you can come to MIT Nano, our facility in the center of campus that now houses a couple of these, or I can tell you about it on the side afterwards. We can chat. It's really cool how it works. By the way, I'm an electrical engineer. It's not like I know about microscopy. I just know how to tell stories about it. So here's another cool image that I'm going to show you. This is a sheet of tungsten diselenide. It's a 2-dimensional material squeezed between 2 other 2-dimensional materials. And there's a picture of that sheet, an edge of it. It's a cool image, but wouldn't it be awesome if I had a video that shows how that image was made, that shows what happens to those atoms as they bounce around and add to the actual formation of the 2D material What would be cool if I only had a video? Oh, I have a video. Now we can make videos of these actual happenings. This is only over the last few years that allows us to see how matter is put together. The reason why the particular atoms are coming on and off is because the electron beam that great engineers figure out how to accelerate electrons to the 70% of the speed of light and then send these electrons through the material you want to investigate. If there's an atom in the way, you won't see that electron, but other electrons will pass through and cast a shadow of the object you're looking at. We are looking at the shadow images of the chunk of matter that happens to be one atom thick, tungsten diselenide. You can see formation of fissures, readdition of the various atoms. Every one of these is really important if I want to reimagine, for example, batteries. Reimagine the way that I'm going to put together the next strongest material in the world. Many options are there. What is stunning to me is asking how much does this truly matter for the advancement of the new ideas? And so if you are going to ask, let's say, set of professors, ask them this. I want to build the next facility for your campus. And that facility should have the tools you need to make the next set of great discoveries. What professors should you have in the room asking that question? Should it be all the Nobel Prize winners we have at MIT? Or should it be someone else? Combination of newer views than the Nobel Prizes? If I had to favor one or the other, which one should I favor? It's a tricky question on purpose. Recently tenured professors are the ones that we just said, we're going to keep you for the next 30 to 40 years. You're defining the future of what MIT is about. Those are the most important professors. Those are the professors I need to make sure succeed in delivering the grand visions of what the world is meant to be. They have a long trajectory of success ahead of them, only if I can support them in the process. They would likely succeed on their own as well. They don't need me. But if I help them, they'll get there faster and they'll get much broader impact than they would on their own. School of Science and School of Engineering and Sloan School, as well, there are two more schools, School of Architecture and School of Humanities at MIT. Those are 5 schools of MIT. School of Science, School of Engineering are the two that would primarily use MIT Nano, our facility for nanoengineering. In a School of Science, 51% of the recently tenured professors need nanoscale to make their advancements. 17% of them will numerically investigate nanoscale, and 34% will actually physically make nanoscale objects. In a School of Engineering, 67% of all of the young professors use nanoscale to make their discoveries. In mechanical, in electrical, in civil engineering, in environmental engineering, you name it. The way the path to the future is through the nanoscale. And we are very much at the dawn of the nano age. Disciplines, any disciplines under a rainbow, is touched by the nanoscale discoveries. Is it medicine and life sciences, like I just alluded to? Is it energy systems, computing and information, various ways of manufacturing, materials and structures, quantum science and technology, and on and on and on. So as we built MIT Nano, it's just a largish space in the middle of campus. We want to make sure that everyone feels welcome, everyone can belong to it, and everyone can get out of it what they need to make their next set of discoveries. So this sounds like I need to figure out how to make a really good innovation hub to make it succeed. Otherwise, I can build a whole bunch of tools, no one will come or few will come, and I won't be able to truly grow those ideas that need to be translated into impact. So we follow the following rules. There are really 3 things you need to do to spur innovation. 1, bring people together of different disciplines. You know that if you think you can invent everything on your own, you might as well stay home and do all your meetings over Zoom. There's no need to step out. But that is not what we find is the most effective way to innovate. It's the crossing of the minds. It's the human friction that gets us to take that next step towards invention we would not ever be able to do on our own. Now, go ahead and make sure that if I'm going to bring you together, you can also easily encounter each other, meaning you also are standing next to me. And third, build an environment so that you're standing next to me, but you're actually willing to talk to me. Actually, you're either bored and you're trying to spend some time chatting with someone, because the deep reactive ion etcher has another half an hour to go, and you're going to tell me about your electrical engineering experiments so I can figure out how I might apply to my biological thinking, because really what I want to do is maybe make a template for growing of neurons so I can make artificial liver or artificial brain or whatever else. And you just told me as an electrical engineer that you have a way of actually patterning the shapes I'm hoping for. Engagement is the key. So we build a space right in the middle of the MIT campus. We build a space that can be easily reached from every corner of the campus. We also made sure that no professor has an office inside MIT Nano, not even the director. Because for as cool as I am, eventually my ideas will get old. Eventually, it better be that the building doesn't age with me. It better be that the building forever stays green as new people step into it with new ideas. The moment you also do that is you make place for everyone. That doesn't belong to anyone, belongs to all of us, to go and support it. So open access and broad reach are the key. The space has clean rooms. Nanoscale is small, so making a room that has no dust is a good thing to consider. Down in the basement are our imaging and metrology facilities. This is where we see those atoms I just showed you. Why in the basement? Because that's the place that doesn't wiggle when the wind blows. And since atoms are small, I want to make sure everything is perfectly stationary. There are more things than simply wind. We have to worry about, like highways passing by and train lines going through and cell phones going off. All of those actually matter to us as well. And then on the top is the prototyping and synthesis place that can take those best discoveries and make them into technological innovations that can change the world. There are about 600 people using it. We opened in 2018, first users arrived in 2019. 6 months later, pandemic started. We recovered from pandemic. At this point, there are about 600 projects happening inside MIT Nano, from about 50 different departments, labs, and centers. I can't tell you what is my discipline, because nanotechnology and nanoscience is not a discipline. It's just the way we do things. It's kind of like asking me, who uses computers today? Everyone does. You do every time you pull out your cell phone. You also, by the way, use nanotechnology every time you pull out your cell phone. I'm just saying. However, we don't often think of it that way. Yet, the key, though, to making those next set of discoveries, right, are ways to translate the academia into something that people can hold in their hands. So we often look on what does it take to go from the invention to 1 million people benefiting from your idea. This is a set of startups started by an MIT-initiated accelerator called The Engine. It's a venture fund that invests into the startups, provides them a little bit of space, but also provides them access to a variety of tool sets available across MIT. MIT Nano, anyone can access. You don't have to be a part of The Engine. We actually have now launched a program we call Star.Nano to allow us to give you discounted rate to use our tools. Because the journey of a startup is a long one and costly one. Well, how long is a good question to ask. Now, let me give you some questions here. How long do you think it took to commercialize zippers? The things you zip your clothes with? Any thoughts? A week? You said a week? More than a week. Yeah, inventions happen quickly, but to actually commercialize it, to make sure you can sell 1 million boots with zippers, took a little longer than that. Any thoughts? A decade, yeah. Yeah, it took 12 years. The first patent was in 1850s, but it was not particularly useful as a patent. In 1913, a modern patent came about, and then 12 years later, you start seeing first clothing applications. And of course, you can look at me and say, well, that's like from the beginning of the 20th century. I mean, really, is that a relevant example? Well, I'm like, yeah, okay, well, why did it take? I mean, buttons are okay. I like buttons, but zippers are so much cooler, right? So what was missing in a zipper to actually allow it not to be commercialized right away? What was missing? Production. Someone said production. There was no, I mean, we knew how to make buttons. And if you are a watchmaker, you knew how to deal with the small mechanical parts. And you would charge a lot of money for every watch you repaired, right? That's not commercially available technology for 1 million people to use. To make a zipper and make it cost nothing, I need ways to manipulate small mechanical parts, put them together precisely over and over again. Tools don't exist for that in the beginning of the 20th century. Tools need to be invented for that. That kind of message repeats itself. Here's another one, Velcro. Yeah, plastics were recognized in the 1940s. In 1950, there's an idea, why don't we go ahead and make curly plastics so they can catch other plastics so you can start having shoes in 1968. It took about 13 years to commercialize Velcro because there was no foundries, no production mechanisms for the extrusion of the plastic fibers that was needed. Today, I can ask you, how long will it take you to make the next silicon chip? And you're going to tell me, that's easy. Intel makes a new one every year and a half. If I want to make a new one, I can ask my students to design it, send it off to TSMC if they take my run, and give it a few months. I can have it wired and packaged, and 6-9 months from now, you can have a new silicon chip made. It sounds like silicon innovation doesn't take a toll that long. How come these guys took 10 years or more? Well, the misnomer about silicon innovation is that it actually took 40 years for you to get here. We spent 40 years building the foundries, developing the tools, so you can use them without inventing a tool, a new layout of your silicon chip. You didn't actually invent anything new when you made that silicon chip. All you did is reshuffle the Lego parts in a different place. That's an important distinction when it comes to new technologies. And it happens to be the defining element of every new hardware startup I had a pleasure to be a part of. We made a mistake every single time to invent a new technology that had no way to be made, causing us then to build a factory as well as a technology. The journey like that repeats itself over and over again. And if you're actually going to kind of try to chart it, you might make a map like this. Down on the bottom is a set of stages. There is a discovery, then early development, then advanced development, then some scale up, and eventually production, right? Those are the stages you need to go through. If you're a startup, all you have is this great idea, academically discovered. The next thing to do is to say, well, I would like to make that idea into something truly useful. And that's when you encounter the first valley of death. Survivability maybe is 10%, meaning only about 1 in 10 ideas will get its initial funding to try that first valley of death. And the venture capitalists that do give you the money, they will not give you all the money you need. They'll give you, of course, just enough money to get you to the next valley of death, where you need to ask for more money. They're doing it because they want to make sure that they don't give you too much money. That's one. And secondly, they know they'll gladly take whatever you can to get to over the first valley to make it to the next. So the next valley of death is once you actually want to make a prototype, well, that's maybe a quarter of the companies get to the luck of actually bringing in the money to get into the prototyping stage. And that's in order so you can get some market traction. It's great to show me pictures that were collected under a microscope that say, this is really good idea, please fund me. All I'm gonna need is a few tens of millions of dollars. Yeah, right. Like I'm gonna fund you for that. Show me a prototype. And once you have me a prototype, next thing you need to show me is that this prototype can be made in million units. That is the scale-up value of death. Not everything, not every brilliant idea you have out there actually is truly scalable. You better keep that in mind before you get to the next stage. if you cross that last valley of death, all you now need to do is actually produce 1 million units and hopefully sell them, and then everything is fine. So no biggie. Very large likelihood of success. 10% times 25% times 33%. What does it come out to? About a couple of percent. Yeah. And the journey takes about 10 years, and it's if you add it all up, it's about $100 million. So it's unlikely anyone in their right mind should give you the money. No. I'm just saying. It's actually, if you go ahead and tell me, I'm going to give you, your first money so you can get going through this whole business of building this company. If I'm going to give it to you in year 1, I expect you to tenfold increase my money. Because I can instead invest that money in a stock market, and historically, I will just about tenfold increase the money that I invested over those years. Just about. If you invest in the right funds and have the right kind of opportunities. You need about 20% year-to-year return to get to that point. So how would you ever actually build a new hardware startup? You can do it because you believe in it. There's a social value to it. That's really hard to convince VCs to give you money for. So the result is that you really can't these days. From the venture capital investments in the United States, I think last year $160 billion were invested, maybe a little more. Of that, only a couple of percent were invested in hardware. Much of it, 90%, is either in healthcare or more likely in digital. Numbers can be corrected, but those are the scales. For me to actually make you the new technology, it's nearly impossible to do so. So what can I do? Well, as MIT Nano, this facility in the middle of MIT, we realized that the 10-year journey actually split in two. This first half of the journey is cheap. It's the second half that's expensive. And if I can make this first half cheaper, that would be even better. If you start a new startup, the very first thing you do is you rent the space off campus, you hire a safety officer to make sure no one gets chemically poisoned. You install a new chemical hood. You bring in a liquid nitrogen tank and have someone actually manage it. All kinds of overhead that indeed will not get you anywhere closer to making your idea work. All it's going to do is spend maybe $3 to $5 million and about a year and a half of everyone's salaries trying to put it all together. Well, why not the day after you graduate, instead of doing that, just step into MIT Nano. I'll charge you nothing, or I'll charge you something that I charge my academic users, maybe a little more, because otherwise my academics will be mad at me. But I can go ahead and come up with a way to bridge that valley of death. I won't make it perfectly flat, because you need to still roll up your sleeves. You need to bring in a seed money. And maybe the first two valleys, rather than costing you 15 million, can cost you 3 million. That's actually a reasonable money to raise from an angel investor or a seed fund. Consequently, being able to step in year 5 or year 6 and say, I have a prototype in my hand. Now I'm ready to really spin out. Or maybe come here and realize this will never scale and stop. Consequently, not spending 15 million on nothing, but spending only 3 million on nothing, much less. The goal is to try more ideas. And for a fraction of the money what it costs now, get more companies to a semi-maturation stage so that more investable opportunities are out there. Anytime the venture capitalist invests money into a company, they've seen 100 other companies before. They are making a really good choice by investing in you when they make an investment. And yet only 20% of the companies succeed. Well, what gives? Did VCs make a bad decision in investing? No. They thought really hard before making your investment. Why did you fail? Well, because 20%, 25% of your success is the technology. 75% is everything else. Do you have a team who's capable? Is it possible to scale the technology? Who are the stakeholders? What's happening in the world outside that you couldn't predict? These are all the reasons why companies fail. It has nothing to do with the quality of what you can deliver or why you initially got invested in. And indeed, we haven't quite figured out how to navigate all of those multitudes of challenges. But one thing for sure is if I give you 100 companies, 20 will succeed. So let me give you 200 companies so that 40 can succeed. That's the premise behind making the first part of a journey much less expensive. I mentioned many ideas, and let me now give you a few of them, unless you have questions. I noticed Scott was letting people interrupt, and I would very much appreciate that, as opposed to just giving you a single stream of thought here. Yes, questions? Yes.
Why, in your opinion, the accent keeps on appearing in most of those nanostructures?
Why does the what? The eczema.
The accent.
The benzene. Because
you can call it benzene if you don't.
Yeah, it's a phenyl ring, 6 carbons. The molecules that we are using in the world we live in are carbon-rich. We are a carbon-based life form. Most of life form, well, all the life forms we know out there are carbon-based. Hence, it is carbon that interacts with us and makes a difference. Unless we are talking about baking soda when we try to make the fluff up of the bread, but yeah, even that has carbon in it, but not rings.
Two-dimensional flat space is covered with that polygon, which is the polygon that's got more edges.
Yes.
Would be possible more information in less space. That's interesting.
It is, although I draw this particular hexagon as flat, it's actually bent. It's twisted. It's either twisted in or it makes like a chair-like shape. It does get flat when it gets incorporated with other benzenes making a graphene sheet, but that's a very special case of this. So then, other questions? Yeah, please.
A quick question on the venture capital. So you mentioned the engine. So are you close to investments from the engine, or are you working proactively with other venture capital from?
You're asking a great question. So the Engine is a venture fund, one of many, many venture funds. We are proud of it as MIT because we kicked it off and we gave it a mission of investing into hard technologies, not just software. And so I mentioned them, but we work with many, many venture capitalists. You probably know that 20% of the venture capital of the world resides in Boston, and about 10% of that money is invested in MIT. Just about a couple of square kilometers around MIT. So we work with many, many venture capitalists. The goal of MIT Nano is to assist anyone who needs help. I have an accent, right? Despite the fact I speak fluent English. 40% of all of our professors at MIT have an accent. Yeah, true. And 40% of all of our graduate students also have an accent. That's because we are very much designed as an institution to serve the world. And our metric is not money we make. We don't make money on anything we do. Thank goodness we have an endowment, otherwise we would go bankrupt. I often say, the profit, our business, right? Our profit on educating undergraduates, I'm told, is minus 87%. Yeah, for every $1 we spend teaching you, we get 13 cents back from intuition. And similarly, graduate students, I think a minus 25% is our profit, I'm told. So thank goodness we have an endowment to actually cover all the losses. So we're not a financially driven institution, we are an impact-driven institution. If our knowledge and our people can change the world, we will attract the next generation of amazing students to join MIT. That's our business. And so if I can, as MIT Nano, support any startup from the world, most likely from the Boston area, and they want to use our facilities, they are more than welcome to. We'll train you, and you can go ahead and use it. Another question?
Yeah, I have a question. How much here?
Thank you.
How much did you need to invest to construct MIT Nano, or is it all private investment by MIT or other?
Yeah, it's all private investment by MIT. The numbers that are listed out there is $350 million to build a facility. It is 10,000 square meters of laboratory space in a 20,000 square meter building. And then inside it, we have at this point about $100 million of tools, and we need another 100 million to fully outfit the space. But we have a lot of tools as is. Yeah, so $500 million. Small money from perspective of impact. There was a question over here.
If you could introduce yourself.
Hi. Hi, so my name is Alba. I work doing data analytics and business intelligence, but I have a dark past doing research in nanophotonics. So my question maybe is a bit technical, and maybe you were going to address it, but so I wanted to ask on your perspective on the end of Moore's law. And for those who don't know it, it's the fact that we are making even smaller. Every year we're making smaller chips. But is there an actual physical limit to it? And what's your perspective?
It's a fantastic question. Just for your own enjoyment, and maybe there will be one more person in the audience who truly enjoys it quite the same way, I'll show you an image I skipped. It is indeed not really coming our way. We have plenty of opportunity. There was a recent development by IBM that showed that 2 nanometer technology. That's more of a really good perspective into the future. The yields are not very high on that technology yet. TSMC states that by the end of this year, they'll make a 3 nanometer, 12-inch scalable technology, which means 6 months later, Samsung will say the same. And so there is a little more to be done there. With that, though, we still have issues with interconnections, both electrical and optical. Optical would be better, right, because we spend most of our energy on actually charging and discharging connection lines. So optical would be awesome to do. But even there, you're still dealing with semiconductors. And you might remember from those of you who took electrical engineering at some point, if you want to change the current through a transistor, you need to apply at least 60 millivolts of voltage. Can't be any less than that. That's called 60 millivolts per decade. Needs to be spent. The less voltage I spend, the better off I would be. So can I make it so it's less than 60 millivolts per decade? You can't. If you can use semiconductors at room temperature, you cannot, physically. Otherwise, you're changing laws of physics. And that's okay, but, hard. So we decided that maybe instead, I can have an on-off of transistor on, transistor off, by not using semiconductors, but by using a little chunk of metal, another surface of metal, and in between, I'm going to squeeze some molecules, 2.4 nanometer tall molecules. If I can bring the top chunk of metal down and squeeze that gap to a smaller gap while applying 0.5 volt between the two of them, can I see some current? And the answer is yes, you can. So that's the plot. That's applying 2 volts, and you can have a very large change in current. Notice how steep that slope is. It's about 10 to 15 millivolts per decade. Much, much steeper than what silicon can ever do. If we can do that, we might be able to make extremely high energy efficiency electronics. But this would take a decade to make real. So I don't think Moore's law is anywhere dead. And I think there are plenty of ideas to follow the conventional Moore's law with the new ways of rethinking it. All right. Well, I can speak for a long time. So rather than do that, let me just give you some other ideas. I mentioned the smell of coffee. And so coming back to that, I was going to show you this image of various types of molecules that make our nose smell things. Is it lemon or raspberry or mint or banana? Notice I drew the benzene just to give you a yardstick again, a meter stick, so you can measure the distances just the same way. And again, you find that every one of these scents is a nanometer-size object. As a matter of fact, notice that orange and lemon molecule up there. It's the same picture. I just twisted it, turned it around by 180 degrees and then flipped it one more time. Same molecule. The only difference between orange and lemon scent is that in one case the molecule is concave, and in the other case it's convex. Fancily, it's known as chirality. What is the chiral twist of the molecule? If you can distinguish between orange and lemon scent, you're distinguishing sub-nanometer features of the molecules. You're designed to experience nanoscale. And it turns out that you do every day, not just by smelling things, but also by reacting. Pheromones, right, are one of those scents that we go ahead and yes, question?
My question is, well, I'm Marcos Martin, as I said before.
Yeah.
My question is, we are in the nano revolution now.
Yes, yes.
Are we going to be in a pico revolution, or what is
Yeah.
next?
Yeah. It's a great question. So the distance between the two atoms is 0.2 nanometers. So I don't really know what to look for smaller than the distance between two atoms. I start getting into nuclear physics at that point. And so, yes, it's good to rearrange atoms, but a single atom to single atom distance is already nanoscale, and that's kind of plenty good. We can see things like those microscope image of bouncing atoms. That is actually 80 picometer resolution in those images, but I need that extra little bit more just so I can see atoms more clearly. That's the only reason why. It's a good question. So pheromones, right, are what we emit to, attract maybe others or respond to others. We don't really recognize it the same way that plants do, because it turns out that plants emit their own hormones. In this case, this is ethylene. It's slightly smaller than a nanometer. But it happens to be the reason why bananas turn from green to yellow, or why apples turn from green to red, or why tomatoes in a greenhouse actually turn ripe. Right? If I have a whole bunch of tomatoes in my greenhouse, I can wait for the first plant to go ahead and give me red tomato, and then I pick that one red tomato, and then go back to my waiting hut and wait for more tomatoes to turn red, and I see the next one and pick. The gardeners don't do that, right? They see the first few plants start giving you red tomatoes, and then they flood the greenhouse with ethylene. That causes the other plants to say, it's time to ripen. It's the way plants talk to each other. And as a result, then all the tomatoes turn red. Like, when in the United States, we spend 1% of our energy cultivating grass in our yards. I don't know if you guys do the same here. About 1% of our fertilizer, energy to make the fertilizer actually goes into fertilizing the lawns, so everything is kind of nice and green. Of course, that means every Sunday you have to go and drive your lawnmower to cut down the grass, because otherwise it grows too tall. Have you guys smelled cut grass before? Yeah. Yeah, what you're smelling is the grass screaming to the other grass, saying, I'm about to be destroyed, save yourselves. And the other grass on the other side of the field starts sending its nutrients to the roots to prevent the cutting from taking away the nutrients. The plants talk to each other by sending nanoscale objects. The smell of the grass is the warning sign. Bumblebees talk to each other by sending smells to each other. Bumblebees, if they want to tell each other there is honey there are good flowers on that side to make honey out of, they send one pheromone, one molecule out. Other bumblebees smell it and say, let's fly to the west. A different molecule, let's fly towards the sun. Another one, we are being attacked. They talk to each other by sending out smells. No, they do it in the best of ways, and they like the smells they send out. So this company, C2 Sense, realized this. If you can detect ethylene by utilizing carbon nanotubes that are dressed in molecules, those are carbon nanotubes, those black smudges, that are dressed in molecules that are selective for ethylene, conductivity of the nanotubes can change when the ethylene attaches to those tubes. If I can measure the conductance by putting an electrode there and one up on the top, I'll be able to tell you, is ethylene in the air or not? Has conductance changed or not? These electrodes, by the way, are painted on a piece of paper. So the whole structure is piece of paper, electrodes, painted carbon nanotubes that are functionalized in a particular way. And now they are deploying it across orchards, apple orchards. Because in the United States, we keep our fruits and vegetables in warehouses before selling it. Apparently 15% of that produce rots before it ever gets sold, because we don't know that a crate in the back has very, very ripe bananas. If we had a sticker on that crate, and the sticker said, there's a lot of ethylene coming out of this crate, you better start selling it, that would save a whole bunch of money. And indeed, orchards are now using it, apple orchards, across the world. I believe Brazil first, to go and use this technology. But so do the pigsties, because you would like to make sure the level of ammonia is low in your pigsty and change the functionalization on your carbon nanotube, and you can have a different molecule detected. There's recent development on nitrous oxide. Anytime your body starts getting sick, it emits more nitrous oxide. I know. If I can monitor that, I can tell you you're about to get sick, or much before you start feeling the symptoms. So opportunities are vast by simply smelling things. Indeed, if you want to detect explosives, this is another way to do it. This was actually used by the US military to detect explosives. Molecules that, upon exposure to TNT, that happens to be a nanoscale object, stop glowing. By observing the glow, you can make a detector for explosive devices that is more sensitive than dog's nose, or just about as sensitive as dog's nose, but doesn't get tired or doesn't need to be fed. We also figured out a way to make it 1,000 times more sensitive than that, again, by using nanoscale ideas on making lasing versions of this. Let me show you this one. This is a technology called a pickle that's electrically excited, and you can get a glow out of it. Now, that's glowing atoms of sodium that you're seeing there. You can make $40 billion if you can take the sliced pickles, lie them side by side, electrically activate them, and sell them as displays. So every one of your cell phones, if you look on it, is a molecular layer that's electrically excited, just like that pickle. It doesn't work at 110 or 220 volts, like that pickle did. Rather, because the distance is so short, you can get away with 3 to 5 volts, and you're going to get a glow out of the molecules. Choose the right molecules, spend 25 years, and you'll get a technology that now commands about $40 billion of the $120 billion display market. That's a transformation of an academic idea that grew into a very important business. The one thing that was missing in that business is actually a way to make it. I mean, those sliced pickles are not easy to handle. And as a matter of fact, we don't handle sliced pickles anymore. We handle molecular species that are synthesized in the lab. The one thing that's missing, though, is an actual manufacturing process to make the high contrast, super thin, ultra fast, pure color, curvable displays. A manufacturing large area nanofabrication process. This is a good idea to give to our students. They go ahead and say, well, why has no one actually built one of these? How come? What needs to be done? And you tell them, well, this is what needs to happen. They're like, no problem. Give me some money, give me some time, and I'll build one of these. This is a startup from MIT, a Cativa, that actually has built the tools. This is how the tool works. It takes a piece of glass, 2 by 3 meters in size, or in this case, 2 by 2 from this older video. And that's a print head that deposits nanoscale thickness of material. Today, every OLED manufacturer uses this tool for some of their steps, one day for all of their steps of manufacturing. And all it is sounded like a crazy idea that requires a whole bunch of validation before it could be actually made into what now encapsulates and now prints active surfaces. That's Jerry Chen. That red square on the wall is the largest piece of glass his company is able to make. Those are smaller pieces of glass that he also handles. The company itself could hence imagine what's next. So they made this video that might now remind you of something you've seen before. It's a phone that opens up. And as it opens up, it can turn into a larger screen. Right? Kind of thin, tiny. That's kind of cool. You can actually buy it like a year and a half ago, 2 years, you can buy it as a shell phone that opens up, right? Well, that was 2 years ago, right? This was made about 7 years ago. this video. Yeah. We knew what was coming based on what we've seen, and we could hence imagine the opportunity that's quite vast and large. You can do it in many different ways. Here's another display technology that was imagined. It looks like nothing here. It looks like a science project. Chunks of stone that glow different colors. These are known as colloidal quantum dots made by Bowendi lab at MIT. And these chunks of stone, you can say, well, they look like nothing that really I can use, except maybe if you spread it, and you spread it very thin on a piece of glass, at which point you can look at an LED light and say, it doesn't look very good. My bananas don't look very good on a conventional LED light. But if I spread on that LED light some quantum dots, these chunks of stone, I can turn some of that blue light into red light. And when my bananas get illuminated, they look much better. I can generate a quality of light that we as humans really appreciate, because finally I can tune it, and yet doesn't necessitate as much energy as before. This is much more energy efficient, and yet color quality exceeds what has ever been done before. Fantastic idea for selling light bulbs. Horrible business. Yeah. Well, I mean, how much can I charge for my little smudge I put on top of an LED? What, 5% of the value of the light bulb? Well, if the LED is $40 a light bulb, like it used to be back in 2009, then 5% is $2. That's good, but that's really good business. Today, though, these LED lights cost only $1. 5 cents goes my way. Really? I mean, I spent 10 cents making it. I mean, I can't. I did bad business. Let me go and think of another business. How about if I can make a light bulb for a TV? If I can make a TV have more beautiful blues and greens and reds, man, that TV can sell like hotcakes out there. People would just want it. And indeed, that's what we've done. We made light bulbs. We sell them for like 25 bucks. I mean, after all, your whole TV is like $1,000, so I can ask you for 25 bucks for my light bulb if your TV is going to look way better. The light bulb is made of gallium nitride LEDs with red and green quantum dots. And if you are doing it well enough, you will find that Samsung really likes it. And then they acquire you. And then they go ahead and take your brand name QLED and say it's ours. So that's what Samsung is doing. And this should say 2022, because it's their flagship products are quantum dot enhanced TVs, invented at MIT, but very much commercialized, very much developed into true product by big companies like Samsung. I'll show you a couple of other ideas, very different from light bulbs. This is a coated surface with a material that prevents stiction, prevents liquid from sticking to it. Now, this would be very important to apply to the following problem. If you have a bottle of ketchup and you want to get the last ounce of ketchup, this is very challenging. However, you can save about 10% of the ketchup of the world by having a bottle coated with a non-sticky material, nanoscale material, edible nanoscale material, allowing you to pour out the very last of your ketchup, hence saving us 10% of the ketchup of the planet. Thank you. Thank you. Thank you. Kripa Varanasi's group in mechanical engineering realized this. They'd actually developed it for a slightly different reason, but this is one that could sell. And actually, they've gotten Colgate to apply it. You can only buy this in Europe, so go on the Colgate shelf and go and find the Colgate toothpaste that gets squeezed out to the last drop. They didn't develop it to make a better toothpaste. They developed it because in steam turbines, when you burn something and generate water to turn into steam, you lose about 15% of energy because of the friction between the steam and the blade of the steam turbine. If I can reduce that friction, I can have much more energy efficient steam generating power generation. If I can reduce the stiction, I can make condensers work far better, and hence your air conditioning would use less energy. That is why his group developed it. They're still trying to commercialize those bigger ideas. Those will take a longer time. In the meanwhile, you might as well launch a little company that makes really good toothpaste looking. You might as well also focus on the following. If you can control stiction, you can also control the pesticides used in the planet. Today, when it comes to watering a plant, we use very small amount of water to actually truly lands on the plant itself. The leaves of the plant are designed to repel the water because it guides the raindrops towards the root of the plant. But the way we water it, it actually doesn't do it very efficiently. So if you can change the stiction, that's conventional spraying. This is the spraying with this very special coating that is introduced in the water itself, making the surface, hence, want to retain the water. You're able to go from this, which is a typical watering, and notice the beading of the water on the leaf, to this, where all the water stays on the leaf. And hence, pesticides that you need to use are dramatically reduced as they're all on the leaf together with the water that was injected. So opportunities are vast, about 10 times reduction in spray volume in the lab. Very much large, and I'll show you two more examples. Again, hopscotching between different technologies. Solar is the other big thing that I'm particularly fond of. I like it because I think we are not thinking of it in the right way. I like solar, and I think it's going to change the planet. If we keep growing it the way it's growing right now, by 2035, all the electricity of the planet, if we can figure out storage, can be provided through sunlight. That's awesome. Now, pardon me for using pounds rather than kilos. 1 pound is 0.45 kilos, so you can divide by this number by 2 and get a sense of kilograms. So 25 kilogram panel of silicon PVs, we think can be converted to a 0.5 kilogram panel of different kinds of PVs. Maybe one's printed on paper. Paper is cool, but it doesn't like water and stuff. So nice idea, and we've done 10 years ago, but it's really not enough to really get you to where you need to go. What would be really cool is to be able to have a high throughput manufacturing, something that can make a technology extremely lightweight. And I'm going to walk to my back to show you an actual example of one of these technologies. For now, you can enjoy this video of us printing one of those active layers of solar cells on top of a piece of plastic. This is what it would take to one day make it as simple as printing the newspapers. Sorry, I'll just grab this. What I want to show you, though, is a technology that is inspired by this idea, making it extremely light, making it extremely simple to manufacture, but not making it meltable underwater like paper would be. All I need to do is take my active layer and put it on a piece of fabric. This is a solar cell. It's made on a piece of fabric. It weighs about 120 times less than silicon. Doesn't rip. The fabric we use is called Dyneema. It was used to pull the ship that was stuck in a Suez Canal. Same fabric, just rolled into fibers, ropes, that was then stronger than steel. And doesn't weigh anything, pretty much. This is what I think can be transformational when it comes to what solar should look like. And why? Well, this is the reason why. There are 1 billion people across the planet without access to grid electricity. And for them to get power, they need to carry it into their village. I bet this individual carrying it doesn't care what's the efficiency of the cell. I bet they care about how many watts per kilogram are they carrying. They can carry 25 kilos on their back. Let's make sure there are a lot of watts behind that. One way to do it is to increase the efficiency. But I can only go so far with efficiency improvements. I'm already at 20% with silicon. Maybe I can make it 30, maybe even 40 if I do some really clever, crazy things. That's only doubling the efficiency. I can 100-fold reduce the weight. That changes the paradigm of installation, delivery, indeed their lifestyle. So we wanted to test this, and we went to India and tested out a whole bunch of opportunities. There are large markets that would make very much difference for this to be deployed. We have also launched a startup. We found a friend in East India, and he started a company called Karma Solar. we sent him a very expensive, flexible, not quite light, but lighter than usual solar cell, and asked him if he can start a business with it. He's indeed opened up one of them here, and he's connecting it to a water pump. Why? Because right now, irrigation is very much needed in the eastern India. And irrigation is typically done by taking a heavy pump and a diesel to run it. Can you transform that? Can you use solar pumped electrical pumps, reduce the weight, and make it much more available while being more environmentally benign? The answer is yes. Karma Solar is doing well and are awaiting our technology to truly be scaled. You can make this technology as light as a soap bubble, actually lighter than such. This is one of these solar cells sitting on top of a soap bubble. But it requires a support, hence why we use Dyneema. The actual cell itself weighs nothing. It's the piece of fabric that gives us the support we need. Now, you looking around the audience are very fashionable people, and you might not like the look of my solar cell, although it does match well my clothing. You might want to choose your own design. I'll help you with that. I'll give you this technology. This is a solar cell enabled through nanotechnology that doesn't look like anything. It's transparent. Actually, still generates 106 volts after being illuminated by sunlight. It works by not absorbing the visible light that our eye sees. But there's other light sun gives us, infrared light, ultraviolet light. Take it and make electricity out of it. And let's test it. Take one of these cells, here it is. Let's connect it to a motor, make sure there's some infrared light in the room. And let's see if we can make electricity. Looks like it works. It does. Every window that you have indeed touched could be this new technology. I'll conclude by showing you one very last technology, and this is acoustics. Rather than solar, rather than LEDs, let me show you how to make a sheet of paper into a speaker. Let's make sure that there is sound. Can you guys hear it? Depending where you point it, you will or will not get the sound. The speaker is as thin as a sheet of paper. It's able to make acoustically audio signal. It's a brand new technology. If you tile it, you can direct the sound where you want it. And as a result, you have the opportunity of making you hear and you not whatever message I'm sending out. In the same fashion, it can work in reverse. You can speak at it, and it will know who and from where is actually delivering that particular speech. If you don't like the noise from your neighbor's apartment, just put this as your wallpaper and you can counteract it. There are many, many other applications. I want to leave you with a simple message, is there are many ways to go. And indeed, our job is to build a better world. Nanotechnology is another in the many opportunities we have. And it is extremely broad. We are at the dawn of the nano age, and it is your inventiveness and those who are working on this technology together with you that will make that next change. Thank you.